Okay, so for this video, we're going to give some motivation for what we're going to be studying next, which are Riemann sums. So let's start with the problem here. Suppose we have some object traveling with velocity given by v of t, and we're interested in the distance traveled over some time interval. For our purposes, we'll just say between 0 and 4. So if we have that the velocity is constant, we know that the distance is equal to the rate times time. So in this case, the distance traveled would just be the 2 meters per second times the 4 seconds. So here is the graph of our velocity function. It's just 2 the entire time. So we know that the distance traveled is rate times time. So in this case, the object would travel 8 meters over that 4 seconds. So that's pretty straightforward. One thing to notice though, since we have that the distance is the velocity multiplied by the time, graphically, this is just the area of this rectangle. The height of the rectangle is the velocity, and the width of the rectangle is the time traveled. So the distance in this case is the area under the velocity curve. So things work out pretty nicely and pretty easily if the velocity is constant. But of course, we don't live in a world where the velocity is constant. So we need to figure out what can we do if the velocity is changing as time changes. So suppose we have a velocity function that looks like this. So we start off with a 0 velocity, but then the velocity increases as the time increases. So our object is speeding up. We want to figure out, well, how can we figure out what the distance traveled by this object is over the 4 seconds? So what we can do is we know how to solve this problem if the velocity were constant. So what if we just assume that the velocity is constant? So we'll break the interval from 4 seconds up into 2 intervals. The first one from 0 to 2, and the second one from 0 to 4. And then the first interval we'll say, okay, we know the velocity isn't constant, but we'll say it's approximately equal to v of 2. And for the second interval, we'll say it's approximately equal to v of 4. So instead of using the blue curve here, which is our actual velocity, we'll use the red lines as our approximate velocity functions. And these are constants, so we know how to work with these. And we can see this isn't a great approximation. For instance, in this area here, in this region, the velocity we're estimating is much larger than the actual velocity. But we'll see how to deal with that in a few minutes. So if we do that, then the distance is approximated by, this should have an approximation here, not an equals, about v of 2 times v of 4 times 2. So notice that would be v of 2 times 2 is the area under this red line here, and the v of 4 times 2 is the area under this. The 2 is the width of those intervals. So here we can see this is also given by these areas under these rectangles. So that gives us an approximation to the distance traveled. Not a particularly good one because we can see we drastically over-approximated the velocity over those intervals. So since we used an over-approximation for the velocity, this is going to be an overestimate of the actual distance traveled. Now, what we can do, though, is if we use smaller intervals, our approximation will be better. So we could see, over here, the approximation isn't terrible. It's over here where the approximation is terrible. So if we use a smaller interval, it would be a better approximation. So suppose we use 4 intervals here. Well, we can see we're still over-approximating the velocity on each subinterval, but it's not as bad. For instance, on this rectangle, yeah, it's definitely an over-approximation, but it's not terrible anymore. And same thing on these ones. They're definitely over-approximations, but they're not nearly as bad as it was in the last one. So here we use 10 rectangles, and now we can see it's an even better approximation than before. So even though the velocity isn't equal to what we're approximating it with on any of these subintervals, they're getting to be better approximations. So here we have with 40 rectangles, and we can see each of these little step functions is much closer to the velocity was than the first one we did. You see down here, they're quite good approximations on this side. And so we went from approximating with 2 giant rectangles, which were pretty bad, to now we use 40 of these little step functions here, and we get a decent approximation for the actual velocity function. So we can see here if we increase the number of rectangles and we just let the rectangles keep increasing, those little step functions get closer and closer to that actual blue curve. So see as we go down here, those step functions get closer and closer to our actual velocity curve. So those become a better and better approximation. Which means since we're getting a better and better approximation to the velocity, if we take the area of those rectangles and add those up, we're getting better and better approximation to the actual distance traveled. So what we can say then is the actual distance traveled is the area under that velocity curve, even when the velocity is not constant. So this area here is our distance traveled. And we just saw we can approximate that with better and better accuracy by using more and more rectangles to get the areas of those rectangles. So let's see, what does this mean in terms of equations instead of just pictures? Well, our first one, when we used two rectangles, we saw the distance traveled was approximately v of 2 times 2 plus v of 4 times 4. And that 2 we saw, that arose because we broke an interval of length 4 up into two subintervals. So the subintervals have length 4 minus 0 because that's the interval, divided by 2, the number of subintervals. So since we're using the right sides of those subintervals, we call this a right-hand Riemann sum. And since there's two subintervals and it's a right Riemann sum, that we'll use R sub 2 to stand for right in two subintervals. So we also saw in our pictures, we used 4 subintervals, 10 subintervals, and 40 subintervals before we went to the animation. So let's look at how to do the formulas for at least 4 and 10 here. So if we have 4 subintervals, we're dividing the interval of length 4 up into 4 pieces. So each subinterval there will have length 1. So our subintervals go from 0 to 1, and then from 1 to 2, and then from 2 to 3, and then 3 to 4. So each of those subintervals has length 1, and they cover the entire interval. And so our right-hand Riemann sub with 4 subintervals, we use the right edge of each of those intervals. So the right edge of this interval is 1, so we have v of 1, and then multiply it by the width, which is 1. For this one, we'd use the right edge, which is 2, and then multiply it by the width is 1. Right edge is 3, right edge is 4. So that gives us our Riemann sum with 4 subintervals. For 10 subintervals, it's a little bit more complicated just because the width of the subintervals isn't quite so nice. So in this case, we have our length is still 4, and we're dividing it into 10 pieces. So 4 divided by 10 is 2/5. So each of our subintervals has length 2/5. So we start at 0 and we go a length of 2/5 over. And then we go from 2/5 and we go another 2/5 over to get to 4/5, 4/5 to 6/5, and so on, until our very last one is going to be 18/5 to 4. So notice 18/5 is 4 minus 2/5. So those are all of our subintervals. And now for our formula for R sub 10, we're going to look at the right edge, which is 2/5, multiply it by the width. So this is the area of that rectangle. 4/5, so v of 4/5, that gives us the height of the rectangle, times 2/5 for the width of the rectangle. And we do this all the way until we get to the last one, which has a right edge of 4 and a width of 2/5. So we could do 40 as well. It's just, the more it gets, it's just more terms to add up. So generally, we'll see later, we usually, if you want to do a sum like this and you want to approximate it with a lot of rectangles, you want to use the computer for that. And notice there's no reason we had to use right edges of the subintervals. We could just easily have used the left edges. You can also use the midpoint. You can use any point in the interval. But for now, we're just going to worry about left and right hand. We'll come back to other ones later. So if we use left hand, the left edge of the interval when we divide it up into 2 would be 0. So we'd have v of 0 times 2 plus v of 2 times 2. So here is the picture of this. So notice there is a rectangle here. It's just since the height is 0, the rectangle has height 0. So we have a rectangle here and a rectangle here, and they touch at the left edge point. And we can see in this case for this function, this is an underestimate of the velocity. So the area with these rectangles is going to be an underestimate of the distance traveled. And again, the more intervals we use, the better the approximation. So here's one with 4 subintervals. Again, since this one has height 0, just as a flat line, but then we have touching on the left edge each time, and so we get a better approximation, but an under approximation. So here's one with 10 rectangles. See, again, it's getting better, and here's one with 40. So just like before, the more subintervals we use, the better the step function approximates the velocity function, which means that better the area of the rectangles approximates the area under that curve, which is the total distance traveled. And when we find the equations for the left-hand sums, we'll use L sub n instead of R sub n to indicate left-hand sum, but it's essentially the same thing except for we use the left edges of the intervals instead of the right edges. So we just saw L of 2 would be 0 and 2 for our edges, and then if we do L of 4, the left edge is 0, then left edge 1, left edge 2, left edge 3, and similarly for 10, you just go from the left edge. And you just have to make sure you're using the right number of rectangles. So notice since we're just doing the left edge here, if we look back at the picture, we don't have a rectangle that touches at 4. The furthest one touches at 3. So we have 4 rectangles at 0, 1, 2, and 3, so we don't touch 4. Just like when we were doing the right hand, we didn't have one that touched at 0. So we just have to make sure you count the number of intervals you're using here and get the right one. So we'll see some more motivation. So this shows us why these types of sums, where we're summing up areas of rectangles, are interesting when we're trying to find the distance traveled. We'll see some other examples of actual applications where this method is useful for physical applications. We can also look at intervals that aren't just 0 to 4. In particular, it's a little bit more complicated if we look at intervals that don't start at 0. So let's suppose we have an interval a comma b, and we have our velocity function still being y equals v of t. So now if we want to do the left-hand Riemann sum or the right-hand Riemann sum with n subintervals, we're going to break this interval AB up into n subintervals, and then the width of these, we take the length of the entire interval, which is b minus a, and divide it by n, so we get n equal subintervals, and we'll label this delta t. So our first subinterval here is going to be, we're going to start at the left edge at a, and then we're going to make that interval be delta t width. So we go to a plus delta t. And so we could also write that as a comma a plus b minus a over n. Now the second subinterval is going to start where the first one ended. So it starts at a plus delta t. And then since we want that to have a width of delta t, we're going to add another delta t to that. So we have a plus 2 delta t. We see we can rewrite that as a plus b minus a over n, comma a plus 2 times b minus a over n. And we can continue to do that for the rest of the subintervals. Now to ease the notation a little bit, we'll say t sub j is a plus j times delta t. And so then our first interval, we know that starts at a, so that should start at t0. And then we want to go to a plus delta t, so that should go to t1. The second one will go from t1 to t2, and so on until we get to the last interval, which is going to be t sub n minus 1 to t sub n. So notice that if we take n times delta t, we get b minus a, so a plus b minus a is b. So that is the right edge of the interval. So then our formula for L sub n and R sub n on this general interval AB is given as follows. So the Ln we know starts, we start our first rectangle at the left edge point of the first subinterval and go until we get to the left edge point of the last subinterval. So that starts at t0 and goes until tn minus 1. And the right Riemann sum, we want the height of our first rectangle to be the value of the function at the edge of the right edge of the first interval, and we go until we get to the right edge of the last interval. So we start at t1 and we end at tn for the right sum. So now we're going to introduce some notation that we refer to as summation notation that will make writing such sums more compact. And so let's start with just a general case where we're not looking at Riemann sums anymore. Let's just look at something a little bit simpler to get the hang of this. So suppose we want to sum the first 100 positive integers. So 1, 2, 3, so on all the way up to 100. So the way we've been writing this up until now is we just say 1 plus 2 plus 3 plus 100. and that dot, dot, dot is supposed to contain all of those terms in the middle. So what we want to do is we want to make this a little bit more compact by using summation notation, where we don't have to use a dot, dot, dot. Now, the summation notation will seem a little bit more complicated at first, but once you get used to it, it's very nice to work with, and you don't have to worry about writing these long expressions out. So that same sum that we had on the previous slide can be written as this. So let's go through each term and see what they mean. So this term here, the new symbol here, sigma, that's called sigma, and it refers to summation. So the j underneath it, the j down here, that tells us that j is our variable for this summation. And the equals 1 says that j is going to start at j equals 1. And then the 100 at the top tells us we're going to start with j equals 1, and we're going to increase j by 1 each step until we get to 100, and then we stop. And then this j in here is the function we're going to evaluate. So when j is equal to 1, we have 1, and then we add the next term, which is j is equal to 2, add the next term, which is j equals 3, so we have 1 plus 2 plus 3, and we keep doing that all the way until we get to j equals 100. So we see we get the same summation, just in a more compact notation as the previous slide. So let's look at an example to make sure we understand how this actually works with a concrete example. So let's look at this one where we start j equals 5, and we're going to go up to j equals 7. And our function here is j squared plus j plus 1. So when we evaluate this, we start with j equals 5. We evaluate the functions. We have 5 squared plus 5 plus 1. And then we add to that the next term. So we evaluate at j equals 6. So 6 squared plus 6 plus 1. We go to the next term, which is 7. So we add on 7 squared plus 7 plus 1. And since we have 7 as our top value here, we stop there. And now we can add all these terms up. And if you do that, you get 131. So we can also go in the other direction where we're already given a summation and we want to write it in summation notation. Now in this case, we could just evaluate what this sum is, and that wouldn't be hard. But the point here is to figure out how we would write this in summation notation. And this is a little bit more difficult than evaluating the summation notation, because that when we evaluate one that we're already given, we're just plugging in numbers and adding them. In this case, this requires pattern recognition, which can be difficult, but you'll get better at it the more you do it. So if we look at just each term and we forget about whether it's positive or negative, we have 2, 4, 8, 16, 32. So you might recognize those as powers of 2. So we have 2 is 2 to the first, 4 is 2 squared, 8 is 2 cubed, 16 is 2 to the fourth, and 32 is 2 to the fifth. So we can think of that as 2 to the j, where we start with j equals 1, and we go all the way up to j is equal to 5. Now the next thing we have to do is figure out those negative signs and how we go from positive to negative to positive to negative to positive, and that's a little bit more complicated. But what we can do is we can see the signs switching with each term. And so if we think of this first term as 2 to the 1, I have minus 1 to the 1 plus 1. The next term, 2 to the 2, notice that would be minus 1 to the 2 plus 1. Third term is minus 1 to the 3 plus 1. So we see if we're thinking of this as 2 to the j, the term out front is minus 1 to the j plus 1. And that works for every single term in our sum. So we can rewrite this sum as the sum from j equals 1 to 5 of minus 1 raised to the j plus 1 times 2 to the j. So let's end this with where we started and look at the velocity function. Say our velocity is t squared, and we're looking on the interval from 1 to 5. And suppose we want to evaluate the left-hand sum L4. So we want to break this interval up into 4 subintervals. So notice the width of our subintervals is going to be the width of the interval, 5 minus 1, divided by how many terms we want to break it up in. So 4. So this is 4 divided by 4. So the width of each subinterval will be 1. So that means our first edge is at 1. And then the width of that subinterval is 1. So the next one is 2, and then 3, and then 4, and then 5. So our 4 subintervals are 1 to 2, 2 to 3, 3 to 4, and 4 to 5. And so now we can evaluate our left-hand sum here. Notice we're doing left edges. So we go left edge of 1, left edge of 2, left edge of 3, left edge of 4. So we start at j equals 0. and we're going to go up to 3. And so we want to evaluate our function v of tj delta t. And so when we evaluate v of t at tj, this is just tj squared. And now notice tj, each one of these is j plus 1. So when it's 0, it's 1. When it's 1, it's 2. When it's 2, it's 3. So tj is just j plus 1. So we can replace that with j plus 1 squared. And then my delta t was just 1. So I have j plus 1 squared times 1. So if we evaluate this then, when j is equal to 0, I have 1 squared. J is equal to 1, I have 2 squared, 3 squared, and 4 squared. And if we add that up, we end up with 30.